Alright, welcome to MA 103's lesson on analytic solution to a system of recursion equations. So in this example, I'm going to go through example 3.7.4 from modeling in a real and complex world, where we're asked to determine the analytic solution and describe the long-term behavior of the initial value problem listed below. And so I've written this out as we're accustomed to seeing our systems of recursion equations expressed as a matrix vector form, right? And so if I'm going to find the analytic solution, then I've got to use two formulas for my formula reference card. The first one is the actual analytic solution, and it looks like this. Oops, let's change that to text maybe. Let's get this worked out real quick. Alt 7, there we go. Alright, so here's our analytic solution, and we should be comfortable with what this says. It says that the vector p sub n is equal to the equilibrium vector plus lambda 1 to the n times c1 times v1 plus lambda 2 to the n times c2 times v2 plus lambda k to the n times ck times vk. And so we know these terms. This is our equilibrium vector. This lambda 1 is the first eigenvalue raised to the nth power. And then this v1 is the corresponding eigenvector. And so that's the same for these other terms, but the only thing that we don't know are these c values. These are constants. And the way that we're going to find these constants is using another equation from the formula reference card. And that looks like this. Let's see here. Right here, so we have p naught minus p star is equal to c1 times v1 plus c2 times v2 plus ck times vk. And so to make sense of this, this p naught minus p star, that's a vector p naught minus a equilibrium vector. So the result of this operation is just another vector, right? And so what we're actually doing here is we're expressing this vector on the left-hand side as a linear combination of the eigenvectors. So we did this in block 2, where we expressed vectors as a linear combination of the standard basis vectors. So it's the same process, it's just this time we're using eigenvectors instead. Okay, and so we can do this. Now to get started solving the problem, we need to go ahead and input our known values here. So I'm going to input our matrix, and I use Control Enter to add a row and Control Comma to add a column. So we'll say 0.8, there should be a 0.5 up there, 0.3 and 0.6. Let me fix this up here. So there's my A matrix, my D vector. Again, using Control Enter there is -1 and 5. And I've got P naught. Initial condition is this vector 8 and 12. And now we're good, right? So we can evaluate this, and my variables turn from red to black. Here's your turn from blue to black, which means you've assigned a value to them. Okay, and so to do this, where we're going to solve for the constants, we've got to know the eigenvectors. So I'm going to go ahead and evaluate the eigensystem, and I'm going to do the same thing that we did with the eigenvector centrality class, where we named the eigensystem M. So eigensystem of A, and we're calling this a matrix M. So there we go. Now I've got my lambda 1 and its corresponding eigenvector v1. This would be lambda 2 and its corresponding eigenvector v2. Right? So now I can take this information, I can substitute it in. Well, not yet, I guess. I gotta find this equilibrium vector too, don't I? And so I'll create a variable called p star, and I'm gonna set that equal to. There's two ways to do this. There's the row reduction method or the inverse method. I'm gonna use the inverse method real quick, which is just the inverse of the identity matrix of 2 dimensions minus A. So the inverse of I minus A times D. So we can evaluate that, and now we have our equilibrium vector. Now we have everything we need to substitute it into this equation. So solve for C1 and C2, I'm going to use a solve command, which will solve a system of equations. So we want to put this in just like you see it on the reference card, or how I have it written up above. Right? And so we're just going to type P0 minus P star double equals. That's a big thing when you're using the solve command. You've got to use a double equal sign in here. It's equal to C1 times this vector V1. But now I've got to put these values in. So what I'm going to do is I'm going to copy and paste. I think it's faster, and I think you're less likely to make a mistake here. So we can paste them directly in. Right, so there's V1 plus C2 times V2. And when we multiply a constant times a vector, we're doing scalar multiplication, so that's why we're using this asterisk symbol and not a dot, right? So go ahead and put in here this V2 value and the second term. All right, and so that's it, right? So P naught minus P star is equal to C1 times V1 plus C2 times V2. And so I can just close off the square bracket and hit Shift Enter to evaluate it, and it's solved for my constants. Some people will show you that you need to put a comma here and tell mathematically you want to find C1 and C2. That's really not necessary since there's two equations and two unknowns. You don't need to do that, right? So we can delete this comma and that statement there. So now that we have our constants, now we just got to substitute all this information into the analytic solution. So I'm going to define it the same way that we do it with our recursion equations. So P bracket N underscore, close the bracket, colon equals, and so it's P star plus lambda 1, which was 1.1 raised to the n. So if you use Shift 6, that would work, or you can hit Control 6 and it will put the exponent up there. So that's what I'm going to do. Looks a little bit cleaner. Times C1. So I'm just going to copy and paste these values so I don't make a mistake. So times C1 times V1. So I've already typed in this vector once. I don't want to waste time copying and pasting the individual terms. I can just copy the vector, right? Plus 0.3, this is my lambda 2. Remember, Control 6 gives me raised to the n. Oops. Times C2, so this term, this value right here, times V2. And again, I had V2 up here in this solve statement, so I'll just copy it and paste. And that's it, right? So I've got P star plus lambda 1 to the n times C1 times V1 plus lambda 2 to the n times C2 times V2. So I'll hit Shift Enter, and now I've got my analytic solution is ready to go, right? So I can solve for P10, and there we are, or I can solve for P100, and I get an answer. And so we can see just from doing P10 and P100 that the system is growing, so it seems to be diverging away from my equilibrium values, which were up here at -30 and -10. But we don't have to iterate like P10 and P100 to know that the system will be diverging. All we have to do is think back to block 1 where we had the linear stability theorem, and we could tell if a system, in block 1 we knew if the system was going to be converging or diverging just by looking at the value of the A parameter. And if the absolute value of A was less than 1, it was going to converge. If the absolute value of A was greater than 1, the system was going to diverge. And that's the same for this block, but all we're looking at is these eigenvalues. If one of these eigenvalues is greater than 1, the system will diverge. And we can look at it down here in the analytic solution. It should make sense. So we've got this equilibrium vector, right, plus this term right here. And so this first term, with lambda 1 being 1.1 raised to the nth power, as n becomes exceedingly large, this whole term that I've highlighted in blue will become exceedingly large, that we're adding on top of the equilibrium vector. So every step of n, we're moving further and further away from the equilibrium vector, right? In contrast, if all of the eigenvalues had been less than 1, we'd have something like we do here with lambda 2. And if I take 0.3 and I raise it to an increasingly large value of n, this whole expression right here will approach 0, right? And so for that reason, if both of these eigenvalues have been less than 1, as n increases, these terms would go towards 0, and all I would be left with is my equilibrium vector, which would mean I'm converging. Okay, and so that's how we develop the analytic solution and how we can classify long-term behavior just by looking at the values or the eigenvalues.